Okay, so welcome to the next in my series on the different gradients and areas that you'll come across in A-level physics. So today I'm going to take a look at some simple harmonic motion, or SHM for short. So let's start off with how we get the first displacement equation for our SHM. So if you're going to get something to oscillate, you need to give it an initial displacement. So we're not talking about forced vibration here, we're not applying something to make it oscillate. All we're doing is displacing it from its equilibrium position and then letting it swing freely. So what we know is it must start with a certain displacement, and it will start with its maximum possible displacement, which we call the amplitude of it. So that's why we know it starts. And then what it's going to do is it's going to oscillate about the equilibrium position in the centre. So that's what we can see here. You've got it initially displaced to its amplitude, and we can see it oscillating about this equilibrium position here. Okay, so because we know it has its maximum at time 0, we know it's going to be a cosine graph, because that's the oscillation graph that we have that has an initial displacement there. So that's what tells us a cosine graph, and the fact the amplitude remains the same as you come across here means we're not doing any work against external forces or damping forces involved here. That's why it stays the same. So that's your displacement graph. So that we've talked about where the amplitude and the cosine comes from, but what about this 2 pi over t section? Well, we know the time period for any kind of oscillation is the time to complete one cycle. So we can see here we've done one full cycle at one time period. Now we also know a full cycle should be 2 pi radians. So putting those two things together, you can see that if you put in time is equal to 1 time period, this becomes cosine of 2 pi, which means you're back where you want to be. So that's where that's come from. And you should also know that time period and frequency are inversely proportional, so you often see it written like this, or even occasionally a cosine omega t, where omega is equal to 2 pi f. You see that occasionally. So that's your displacement graph. So let's have a look at where some gradients come into this. Okay, so we've got the same graph as before, and if you think about what the gradient represents, well, our unit on the y-axis is meters, and our unit on the x-axis is seconds, so the gradient will have units of meters per second, which means it's a velocity. Okay, so we know the gradient of our graph is going to be the velocity of the object. So if we want the gradient, what we're going to do is take the equation of the graph and take the derivative with respect to whatever's on your x-axis here, which in this case is time. So you should, if you're sort of at A2 level in maths, have come across how to deal with trigonometric functions. If you haven't, you will do. But that's what I'm applying here. So what I'm doing is taking the derivative of the displacement with respect to time, and we end up with this expression here. So the derivative of the cosine function is a minus sine function. Your t is multiplied by this, so that comes outside as well. And you end up with this function for velocity there, and that's the gradient of that graph. Okay, so in terms of what that looks like, your velocity graph will look like this. So it's a sine graph, so you can see it will start at 0, 0, but it's a minus sine graph, so instead of going up first, it will go down first in that section there. But we still have the same features we had before to make one time period the same as 2 pi radians. Now, we look at the gradient of this graph. The y-axis, we have a unit of meters per second. X-axis, we have a unit of second, which means the unit of the gradient is meters per second squared, which means it's an acceleration. Okay, so again, same process as before. If we want the gradient, we need the derivative of the equation of the graph with respect to what's on the x-axis. So that's what you can see going on here. And then again, we get down to this equation right here, the equation for the acceleration of an object. Okay, so one of the things you should know about SHM is that the acceleration should be directly proportional to the displacement, but in the opposite direction. So let's take a look at that over here. So if we look at the graph, we can see that this one's going to be a minus cosine graph, this is a cosine graph. So we can see where the directly proportional part comes in, but we can see this one was always negative and that was positive, so we know it's in the opposite direction, so that's kind of working. And if we look at the equation here, this is your equation for acceleration. So you can see you've got a cosine 2 pi over t times the time. that is the displacement. So we can replace all of this with just a displacement, which is what we've got here. And this is the form you'll sometimes see. This is like a equals minus k squared x. You'll often see that, or some other variant. Essentially, you've got this relationship. So we know acceleration is in the opposite direction, but is directly proportional in terms of magnitude to displacement, because these are all constants in here. So that's how we can see it both graphically and in terms of some calculus. Okay, so with all of these videos about gradients of areas, I always finish on something a little bit more tasty. So one of the questions I often get from my class on SHM is you have this equation for velocity in your formula sheet here, and they want to know where it comes from. So we've talked a lot about a gradient so far, so now we need to talk about area under graphs. Okay, so we have this equation here relating acceleration and the displacement. So what we're going to think about is how we can then turn that back into a velocity. So one way you can turn an acceleration into velocity is to integrate with respect to time. But as you see here, none of the things in this equation are functions of time, so that's not going to help us too much in this case. So what we're interested in getting is an equation that calculates the velocity at a certain displacement. So what we need to think about is how we can get that. So what some of you may or may not know is you also have another equation for calculating acceleration using derivatives. So the acceleration is the velocity times the rate of change of velocity with respect to the displacement, so not rate with in terms of time. I shouldn't really have said rate of change because that implies time actually. So the derivative of velocity with respect to displacement is better. Okay, so those of you unconvinced by that, take a look at the units of the properties and you'll see that that works, but that's a bit of an odd one you might have seen before. So what we can do is we can move this dx over to the other side, and if we want to get rid of these partials, what we need to do is integrate. So that's what I've done. I've moved the dx, as we can see, into the acceleration side, and we're going to integrate this one with respect to v, and this one with respect to x, because those are the partials that we've got there. So the key here is deciding what your limits are. So when you start the whole pendulum swinging, you start from the amplitude. So in terms of displacement, you can see we started from the displacement equals amplitude in the integration. At the amplitude, the velocity is 0, which is why we started the velocity at 0 here. We want to know what the velocity is at a certain displacement x. So if we put x in here, we want to know what the velocity is there. So now we can go ahead and integrate those two sides, which is where these expressions come from. Obviously this one you're going to end up with subtracting 0, which I haven't shown it, and then we end up with this on this side here. So what you can see straight away is all your halves are going to cancel out, and if we square root this expression here, 4 pi squared over t squared, I've got a stray a has appeared in my equation for some reason. Let's get rid of that. So we can just square root that, that gives you 2 pi over t, and then in here we have square root of a squared minus x squared to get rid of that minus sign there. And that's where this equation in your formula sheet comes from. It's from doing an integration of your acceleration with respect to the displacement there. And hopefully you found that interesting. So as usual, if you spotted anything wrong or you want some clarification, please do put a comment in below the video. And thank you very much, as always, for watching.